somewhere in the Milky Way, a star is losing mass equivalent to the entire Earth every single month. Not through some quiet, gentle breeze of particles, the way our sun sheds its solar wind, but through a violent, screaming gale of superheated gas moving at 9 million kilometers per hour. The material ripped from this star's surface is so hot, so energized, that it glows with the fury of 100,000 suns. And yet, to this star, the loss barely registers, because this star is so colossally massive, so absurdly luminous, that it makes our sun look like a flickering candle placed beside a raging forest fire. This star belongs to a class of objects so extreme, so rare, and so temporary that fewer than a dozen are known to exist in our entire galaxy. It is a hypergiant. And if it survives long enough, it will strip itself down to its blazing core, shed every last vestige of its outer atmosphere, and transform into something even stranger, a Wolf-Rayet star, a naked stellar engine burning at temperatures that would vaporize anything within billions of kilometers. These are the largest, most luminous, and most violent stars in the known universe, and almost every single one of them is a ticking bomb. Consider what it means to hold 30 Earth masses of material in your hand and throw it all away. Not over the course of a century, not over a decade, every single year, for thousands of years on end. That is what these stars are doing. They are spending themselves with a ferocity that borders on the absurd, pouring material into the void at rates that would empty most stars in a geological instant, and they can afford to do it because they started with so much. The most massive hypergiants begin their lives with 100, 200, or even 300 times the mass of our sun. They are born enormous, and everything that follows, every eruption, every brightening, every catastrophic shedding of their outer layers, is a consequence of that initial excess. When we look up at the night sky, most of the stars we see are modest things. Our sun, a yellow dwarf, is a perfectly ordinary star. It has been burning hydrogen in its core for about 4.5 billion years, and will continue doing so for roughly another 5 billion. It is stable. It is predictable. It is, frankly, boring, at least by the standards of what the universe is capable of producing. The stars we are about to discuss exist at the opposite end of every conceivable scale. They are millions of times more luminous than the sun. Some of them are so physically large that if you placed them at the center of our solar system, their surfaces would extend past the orbit of Jupiter, past Saturn, and in some cases would swallow everything out to the orbit of Neptune. Their lives are measured not in billions of years, but in millions, and the most extreme phases of their existence last only a few 100,000 years, or even less. They are the rarest objects in the stellar zoo, the fleeting monarchs of a cosmos that does not tolerate excess for long. And their stories are among the most dramatic in all of astrophysics. To understand what makes these stars so exceptional, and why their existence pushes against the very limits of what physics allows, we need to start with a simple question, one that has a surprisingly complicated answer. What exactly is a hypergiant? And what separates these stellar titans from the merely large? The answer begins with the way astronomers classify stars, a system that has been evolving and refining itself for well over a century. In the early 1900s, two astronomers working independently on opposite sides of the Atlantic Ocean made a discovery that would transform our understanding of stellar populations. Ejnar Hertzsprung, a Danish chemist turned astronomer, and Henry Norris Russell, an American astrophysicist at Princeton, both realized that if you plotted stars on a graph according to their temperature and their intrinsic brightness, something striking happened. The stars did not scatter randomly across the chart. Instead, they clustered into distinct groups, revealing hidden patterns in the stellar population that had not been apparent before. The diagram that bears their names, the Hertzsprung-Russell diagram, or HR diagram, remains one of the most important tools in astrophysics. It is, in essence, a map of stellar evolution, showing where stars of different masses, ages, and evolutionary states reside in the two-dimensional space of temperature and luminosity. Most stars fell along a diagonal band that became known as the main sequence, a strip running from hot, bright blue stars in the upper left to cool, dim red stars in the lower right. Our sun sits comfortably in the middle of this band, a yellow dwarf of moderate temperature and luminosity. Stars on the main sequence are in the prime of their lives, fusing hydrogen to helium in their cores, in a state of stable equilibrium that can last for millions to billions of years, depending on their mass. But above the main sequence, in the upper reaches of the diagram, there were other stars. Stars that were far brighter than their temperatures alone would suggest. These were the giants and the supergiants, stars that had swollen to enormous sizes as they aged and burned through their nuclear fuel. They had left the main sequence and embarked on the final chapters of their existence. Chapters that would play out far more rapidly and far more violently than the long, placid years of hydrogen burning that preceded them. The classification system that emerged divided stars into luminosity classes, designated by Roman numerals. Main sequence stars received class 5. Giants received class 3. Bright giants, class 2, and supergiants, the truly luminous and massive stars, received class 1, which was further subdivided. Class 1b designated ordinary supergiants. Class 1a designated the more luminous ones, and then, sitting at the very top of the diagram, occupying the most extreme corner of stellar real estate, were the hypergiants, sometimes designated luminosity class 0 or 1A+. These were the stars that pushed against the ultimate physical boundary governing stellar luminosity, a threshold called the Eddington limit. The Eddington limit, named after the brilliant British astrophysicist Arthur Eddington, represents a fundamental tug of war at the heart of every star. Eddington, who made groundbreaking contributions to our understanding of stellar structure in the early 20th century, realized that there must be an upper boundary to how bright a star can be. The reason is elegant and physical. Gravity pulls the star's material inward, trying to collapse it into the smallest possible volume. Radiation pressure, generated by the nuclear furnace in the core, pushes outward, trying to blow the star apart. In a stable star like the Sun, these two forces are in near-perfect balance, and the star can persist in this equilibrium for billions of years. But as a star becomes more massive, its core burns hotter, and the radiation pressure increases dramatically. The relationship between mass and luminosity for main sequence stars is steep. Roughly, luminosity scales with the third or fourth power of mass. A star 10 times the mass of the Sun does not shine 10 times brighter. It shines roughly 10,000 times brighter. A star 50 times the mass of the Sun can shine hundreds of thousands of times brighter. At a certain point, the outward pressure of light itself becomes so intense that it begins to physically lift material off the star's surface. Individual photons, each one carrying a tiny quantum of momentum, collectively exert enough force on the atoms in the star's outer layers to overcome the gravitational pull holding them down. This is the Eddington limit. A star shining at or above this limit is essentially tearing itself apart with its own light. The Eddington limit depends on the star's mass and composition. For a star made primarily of ionized hydrogen, the limit is roughly 33,000 times the Sun's luminosity per solar mass. For a star of 100 solar masses, this works out to about 3.3 million solar luminosities. But real stars are more complex than simple ionized hydrogen, and effects like the opacity of heavy elements in the star's atmosphere can modify the effective Eddington limit, sometimes reducing it significantly. In the iron-rich outer layers of a very massive star, the many absorption lines of iron ions can dramatically increase the opacity, lowering the effective Eddington limit and making the star even more prone to instability. This iron opacity effect is believed to be one of the driving forces behind the dramatic variability of luminous blue variables and the eruptions of hypergiants. Hypergiants live right at this edge. Their luminosities are so extreme, often millions of times that of the Sun, that the radiation pouring through their photospheres is nearly strong enough to overcome gravity entirely. The result is spectacular instability. These stars do not sit quietly. They pulsate. They erupt. They shed vast quantities of mass in violent outbursts that can rival the brightness of a supernova. And because they are burning through their nuclear fuel at such a prodigious rate, their lives are astonishingly brief by stellar standards. A hypergiant might live for only a few million years before exhausting its supply of fusible material and meeting a catastrophic end. For comparison, our Sun has been around for nearly 5 billion years and has barely reached middle age. A hypergiant would burn through its entire life cycle in a fraction of 1% of that time. But within the broad category of hypergiants, there is enormous diversity. These stars come in different colors, different temperatures, and different stages of their brief but dramatic lives. And each type tells a different part of the story of how the most massive stars in the universe live, evolve, and ultimately die. Astronomers know of only about 10 hypergiants in the entire Milky Way galaxy, which means that Sun-like stars outnumber them by more than 1 billion to 1. Even this small number is probably an overcount in some ways and an undercount in others. The thick dust that pervades the plane of the Milky Way hides many of these stars from view at visible wavelengths. And it is only through observations in infrared and radio wavelengths, which can penetrate the dust, that many hypergiants have been discovered at all. Beyond the Milky Way, astronomers have identified additional hypergiants in the Magellanic Clouds, the two satellite galaxies that orbit our own. These nearby extragalactic examples have been invaluable for understanding the properties of hypergiants. Because the distances to stars in the Magellanic Clouds are much better constrained than the distances to stars embedded in the dusty confusion of the Milky Way's disk. A 2022 study led by Michalis Kerniotis from the Czech Academy of Sciences found that several hypergiants in the Magellanic Clouds share a common property. They are pulsating. Their brightness changes in repeating patterns as they throb in and out, swelling and contracting with periods of months to years. This pulsation may be linked to the mechanism by which hypergiants eject material, with each expansion cycle potentially driving a new episode of mass loss. The connection between pulsation and mass loss in hypergiants remains an active area of research, and understanding it is key to predicting the future evolution and ultimate fate of these extraordinary objects. Let us begin with the largest among them, the red hypergiants. These are the titans of physical size, the stars whose sheer dimensions defy easy comprehension. When astronomers talk about the biggest stars in the universe, they are almost always talking about red hypergiants and red supergiants, the bloated, aging monsters that have expanded to truly staggering proportions as they approach the end of their lives. The process that creates a red hypergiant begins on the main sequence, where all stars spend the majority of their lives. But even in this initial phase, the progenitors of red hypergiants are extraordinary. A star that will eventually become a red hypergiant starts out as one of the hottest and most massive types of star, an O-type or early B-type star, blazing blue-white with surface temperatures exceeding 30,000 degrees Kelvin. These O-type stars are themselves remarkably rare, constituting less than 1% of all stars in the galaxy. They are so luminous that they can be seen across vast distances, serving as beacons that mark the spiral arms of galaxies. They ionize the gas around them, creating glowing nebulae that light up like neon signs across thousands of light years. And they live fast. While our sun has a main sequence lifetime of roughly 10 billion years, an O-type star may exhaust its core hydrogen supply in as little as 3 to 5 million years. In the time it takes the Earth to orbit the sun a few million times, these stars have already lived and died. These stars are already enormous by most standards, perhaps 15 to 40 times the mass of the sun, and hundreds of thousands of times more luminous. But they are also compact, relatively speaking, with radii only a few dozen times that of the sun. The real expansion comes later. When such a star exhausts the hydrogen in its core, something remarkable happens. Nuclear fusion slows, and the core contracts under gravity. This contraction heats the surrounding layers, igniting hydrogen fusion in a shell around the now helium-rich core. The energy generated by this shell burning causes the outer layers of the star to inflate dramatically. Astrophysicists call this the mirror effect. As the core contracts, the envelope expands. And the expansion is not subtle. The star swells to hundreds or even thousands of times its original radius. Its surface cools as it expands, shifting from blue-white to yellow to orange, and finally to deep red. The surface temperature may drop from 30,000 Kelvin to around 3,500 Kelvin, cooler than many household incandescent light bulbs. The star has become a red supergiant, and if it is massive enough and luminous enough, a red hypergiant. What is remarkable about this transformation is the sheer scale of the expansion. On the main sequence, a massive O-type star might have a radius of perhaps 10 to 15 times that of the Sun. As a red hypergiant, the same star can inflate to a radius of 1,000 to 2,000 solar radii. The star has expanded by a factor of 100 or more in radius, and its volume has increased by a factor of 1,000,000. This is not a slow, graceful swelling. It unfolds over a cosmically brief timescale of just a few tens of thousands of years, a blink of an eye in the life of a galaxy. And during this expansion, the star's outer envelope becomes dominated by a deep convective zone, a churning, turbulent layer that extends over roughly 99% of the total radius and 60 to 70% of the mass. It is this convection, this roiling internal weather, that drives the enormous pulsations and mass loss events that define the red hypergiant stage. The most famous of these red hypergiants is VY Canis Majoris, a star that has captivated astronomers for over 2 centuries, located roughly 3,900 light-years from Earth in the constellation Canis Major. VY Canis Majoris is one of the largest stars known in the Milky Way. Its radius is estimated at roughly 1,420 times that of the Sun. To put that in perspective, if VY Canis Majoris were placed at the center of our solar system, its surface would extend well past the orbit of Jupiter. Light traveling at 300,000 kilometers per second would take more than 8 hours to circumnavigate this star. Our Sun, by comparison, can be circled by light in about 14.5 seconds. But VY Canis Majoris is more than just large. It is also wildly unstable. The star is surrounded by a complex, asymmetric nebula of ejected material, the debris of violent mass loss episodes that have been stripping the star of its outer layers for thousands of years. Observations with the Hubble Space Telescope and the ALMA Radio Telescope array in Chile have revealed that this mass loss is not smooth or uniform. Instead, VY Canis Majoris ejects material in arcs, loops, knots, and jets, structures that astronomers have compared to coronal mass ejections on our Sun, except scaled up by a factor of roughly 1 billion. Every year, VY Canis Majoris loses mass equivalent to about 30 times the mass of the Earth, flung outward by enormous convective cells that blast through the star's photosphere like bullets. Roberta Humphreys, an astronomer at the University of Minnesota, who has spent decades studying this star, has noted that 6 distinct outflow events have been identified over the star's last 25 years of active mass loss. The current period of intense activity appears to have begun roughly 1,200 years ago, possibly triggered by a structural change deep within the star's convective layers. VY Canis Majoris is losing weight, and it is doing so violently. Humphreys and her colleagues have observed changes in this star on timescales of a human lifetime, a remarkable statement for a field where most processes unfold over millions or billions of years. As Humphreys has noted, VY Canis Majoris is expected to go supernova within the next 100,000 years. And when it does, it could produce a type 2N supernova, a hypernova, or possibly collapse directly into a black hole. For a long time, VY Canis Majoris was cited as the largest known star, but measurements of stellar size are notoriously difficult, and the record has changed hands several times. Another contender that held the title for years was UY Scuti, a red supergiant located roughly 9,500 light-years away in the constellation Scutum. When UY Scuti was first measured in 2012, its radius was estimated at 1,708 solar radii, making it one of the most enormous stars ever recorded. However, more recent measurements using data from the European Space Agency's Gaia mission have revised the star's distance downward, which in turn reduces its calculated luminosity and radius. Current estimates place UY Scuti's radius at roughly 755 solar radii. Still enormous, but considerably smaller than VY Canis Majoris. This kind of revision is common in stellar astronomy, and it illustrates one of the fundamental challenges of studying these distant and obscured objects. The current strongest contender for the title of largest known star, though the claim is debated, is Stephenson 2-18, also known as Stephenson 2 DFK1 or RSG C2-18. This red supergiant or possible red hypergiant sits near the open cluster Stephenson 2 in the constellation Scutum, at a distance of roughly 19,000 light-years from Earth. Its estimated radius of approximately 2,150 solar radii would make it truly colossal. If placed at the center of our solar system, its surface would extend nearly to the orbit of Saturn. Its volume would be over 10 billion times that of the Sun. However, these measurements come with significant uncertainty. The star's distance is not precisely known. Its membership in the Stephenson 2 cluster is debated, and its spectral energy distribution is peculiar. Some astronomers have argued that the radius estimate may be inflated due to incorrect assumptions about temperature or distance. The title of largest star remains an active area of investigation, and it may change again as more precise measurements become available. Another magnificent example of a red hypergiant is Mu Cephei, sometimes called Herschel's garnet star because of its strikingly deep red color. Located roughly 2,800 light-years from Earth in the constellation Cepheus, Mu Cephei is one of the largest and most luminous stars visible to the naked eye. Its radius is estimated at between 972 and 1,200 and 60 solar radii, depending on the measurement technique used. William Herschel, who observed the star in the 18th century, described its color as garnet, and it remains one of the most intensely red stars visible without optical aid, like VY Canis Majoris. It is a semi-regular variable star, pulsating slowly over periods of hundreds of days. And like all red hypergiants, it is approaching the end of its life, destined to explode as a supernova in the astronomically near future. Perhaps within a few 100,000 years. There's also NML Cygni, another extraordinary red hypergiant located roughly 5,300 light-years away in the constellation Cygnus. With a radius estimated at around 1,650 solar radii, NML Cygni rivals VY Canis Majoris in size. It is one of the most luminous cool stars in the Milky Way, shining with a luminosity of roughly 270,000 suns. Like VY Canis Majoris, it is a powerful source of maser emission, radio frequency radiation, produced by excited molecules in its circumstellar envelope. The presence of these masers tells us that the star is surrounded by dense clouds of expelled gas and dust, the signature of extreme mass loss. What all of these red hypergiants share is a sense of being on the edge. They are the largest structures that a single star can achieve, pushed to the limits of what stellar physics permits. Their outer layers are so loosely bound by gravity that the slightest perturbation, whether from internal pulsations, convective upheavals, or interaction with companion stars, can send enormous quantities of material cascading into space. They are stars in the process of stripping themselves bare, and the material they shed will eventually become the raw ingredients for new generations of stars and planets. In this sense, the death of a hypergiant is also an act of creation, seeding the galaxy with the heavy elements forged in its nuclear furnace and scattered by its violent demise. But not all hypergiants are red and bloated. At the opposite end of the temperature spectrum lie the blue hypergiants and their close relatives, the luminous blue variables. If the red hypergiants are the largest stars by physical size, the blue hypergiants are among the most luminous and most massive. They burn hotter, shine brighter, and die even faster than their red counterparts. And they are, if anything, even more unstable. A blue hypergiant is a massive star with a surface temperature exceeding 10,000 degrees Kelvin, sometimes reaching well above 20 or 30,000 degrees. These stars are extraordinarily luminous, often shining with the light of millions of suns. Unlike the red hypergiants, which achieve their enormous sizes through expansion and cooling, blue hypergiants are relatively compact but ferociously energetic. Their luminosities place them at or near the Eddington limit, which means they are constantly on the verge of blowing themselves apart. One of the most famous blue hypergiants is the Pistol Star, located roughly 25,000 light-years from Earth, near the center of the Milky Way. Discovered in the early 1990s using the Hubble Space Telescope by astronomer Don Figer. The Pistol Star was initially believed to be one of the most luminous stars ever found, with estimates placing its luminosity as high as 10 million times that of the Sun. Subsequent studies have revised this figure downward. But even at a more conservative estimate of roughly 1.6 to 3.3 million solar luminosities, it remains one of the brightest stars in the galaxy. Its mass, while uncertain, is estimated to have been as high as 200 solar masses at birth. Though it has lost a significant fraction of that mass through its intense stellar wind, the Pistol star takes its name from the Pistol Nebula, a shell of ejected gas that surrounds it. This nebula, roughly 4 light-years across, comparable to the distance from our Sun to the nearest star, was created by enormous eruptions from the Pistol star over the past several thousand years. The star expelled material so violently that the resulting nebula contains several solar masses worth of gas and dust. If the Pistol star were not hidden behind thick curtains of interstellar dust near the galactic center, it would be visible to the naked eye as a 4th magnitude star, easily spotted on a clear night. Instead, it can only be observed in infrared light, which can penetrate the dust that blocks visible wavelengths. The Pistol star is classified as a candidate luminous blue variable, or LBV, a particularly dramatic and unstable phase in the life of a very massive star. Luminous blue variables are among the most spectacular objects in the stellar zoo. They are massive, hot, and enormously luminous. But what sets them apart is their variability. LBVs undergo dramatic changes in brightness and temperature over periods of months to years, shifting back and forth across the upper reaches of the Hertzsprung-Russell diagram. During quiescent phases, they may appear as hot, blue supergiants. During active phases, they can cool and expand significantly, brightening by 1 or 2 magnitudes as their effective temperature drops. And during their most extreme episodes, known as giant eruptions, they can briefly rival a supernova in luminosity, while ejecting enormous quantities of mass. The class of luminous blue variables takes its modern name from a 1984 talk by the astrophysicist Peter Conti, who united several previously separate categories of variable massive stars under a single banner. Before Conti's classification, these stars had been known by various names depending on where they were studied. In the Milky Way and the Magellanic Clouds, they were called S. Doradus variables, after the prototype S. Doradus in the Large Magellanic Cloud, one of the most luminous stars in that galaxy. In the more distant galaxies, Messier 31 and Messier 33, they were known as Hubble-Sandage variables, after Edwin Hubble and Alan Sandage, who had identified irregular variable stars of exceptional brightness in those galaxies as early as the 1920s. And the Northern Hemisphere prototype P Cygni, a luminous blue variable in the constellation Cygnus, had been known for centuries as a peculiar variable star. P Cygni erupted dramatically in 1600, suddenly appearing as a 3rd magnitude star, where previously there had been nothing visible to the naked eye. It faded, brightened again in the 16th century, faded again, and has been slowly brightening over the past few centuries. Today, it hovers around 5th magnitude, visible to the naked eye from dark sky locations. P Cygni lent its name to a distinctive spectral line profile, the P Cygni profile, characterized by a combination of emission and blue-shifted absorption in the same spectral line. This profile is the telltale signature of material flowing outward from a star, and it is seen in virtually all luminous blue variables and many hypergiants. Only about a dozen confirmed luminous blue variables are known in the Milky Way, a testament to both their rarity and the brevity of the LBV phase, which is estimated to last less than 100,000 years. Their importance to our understanding of massive star evolution, however, far exceeds their numbers. LBVs are widely believed to represent a critical transitional phase between the main sequence and the Wolf-Rayet stage for the most massive stars. During this phase, the star sheds the last remnants of its hydrogen envelope through a combination of steady stellar winds and violent eruptive mass loss, preparing it for the final stripping that will expose its helium-burning core and transform it into a Wolf-Rayet star. The prototype of this class, and arguably the most extraordinary star in the Milky Way, is Eta Carinae. Located roughly 7,500 light-years from Earth in the southern constellation Carina, Eta Carinae is a binary star system containing at least two massive stars. The primary star alone has a luminosity estimated at roughly 5 million times that of the Sun, and a mass thought to be around 90 times solar, though it may have started its life with as much as 150 to 250 solar masses. The secondary star, while less well understood, is also extremely massive and luminous, probably an O-type star with a mass between 30 and 80 times that of the Sun. The two stars orbit each other in a highly eccentric orbit with a period of about 5.5 years. Eta Carinae became famous for an event that took place in the 1840s, an episode now known as the Great Eruption. The star had been known to European astronomers since at least the 17th century, when Edmund Halley catalogued it as a fourth magnitude star in 1677. For over a century after that, it appeared unremarkable, just another moderately bright star in the far southern sky. But in the 1820s, things began to change. The star brightened noticeably in 1827, reaching roughly first magnitude before fading again. Then, in late 1837, the astronomer John Herschel, who was conducting an extended observing campaign from the Cape of Good Hope in South Africa, was astonished to see that Eta Carinae had brightened dramatically, outshining Rigel, one of the brightest stars in the sky. The brightening continued into 1838, when the star briefly matched the brightness of Alpha Centauri, the closest star system to Earth. But the real spectacle was yet to come. In March of 1843, observers across the southern hemisphere watched in astonishment as Eta Carinae surged to become the second brightest star in the entire night sky. The Reverend W.S. Mackay, writing from Calcutta to Herschel, reported his amazement at the transformation, noting that the star had become fully as bright as Canopus and resembled Arcturus in color and appearance. Observations at the Cape of Good Hope confirmed that the star peaked in brightness between March 11 and 14, 1843, surpassing Canopus and falling just short of Sirius. At its maximum, Eta Carinae likely reached an apparent magnitude of -0.8 to -1, an extraordinary brightness for a star located thousands of light years away. For comparison, a typical supernova in our galaxy would be expected to reach similar brightness. But this was no supernova. What made this event so extraordinary was that Eta Carinae survived, despite releasing nearly as much visible light as a supernova explosion. Eta Carinae survived. The star did not blow itself apart. Instead, it ejected a vast quantity of material, estimated at somewhere between 10 and 45 solar masses of gas, at speeds of up to 650 kilometers per second. Some of the fastest material detected in more recent studies was moving at speeds of up to 3,500 to 6,000 kilometers per second, suggesting a blast wave component to the eruption. This ejected material formed the Homunculus Nebula, the distinctive bipolar cloud of gas and dust that now surrounds Eta Carinae and gives it its characteristic double-lobed shape. Each lobe of the homunculus spans about 1 light-year and continues to expand at roughly 1.5 million miles per hour. The cause of the Great Eruption remains one of the great mysteries of stellar astrophysics. The most popular hypothesis suggests that the star's luminosity temporarily exceeded the Eddington limit, generating radiation pressure so intense that it physically blew off the outer layers. But some researchers have proposed that the event may have been triggered by something far more dramatic. Perhaps a deep-seated hydrodynamic explosion within the star, or even the merger of 2 stars in what was originally a triple system. A team led by Nathan Smith of the University of Arizona has proposed this merger hypothesis, noting that it could explain the bipolar shape of the ejected material and the energies involved. The Great Eruption may have been less like a wind-driven mass loss event and more like a genuine explosion, comparable in kinetic energy to a supernova, but somehow non-fatal to the star. NASA's Chandra X-ray Observatory has been monitoring Eta Carinae for over 2 decades, building up a time-lapse movie of the expanding debris from the eruption. These observations, spanning data from 1999 to 2020, have revealed that the Great Eruption was not a single event. The Chandra data suggest that material was ejected from the star in at least 2 separate explosions, one occurring sometime between 1200 and 1800, and another during the observed eruption of the 1840s. The fast blast wave from the second eruption is now catching up to and interacting with the slower-moving material from the first, creating a ring of X-ray emission that continues to expand and brighten. Today, Eta Carinae is still very much alive and very much unstable. It has been gradually brightening since about 1940, and by 2014, it had exceeded magnitude 4.5, approaching naked eye visibility once again. Astronomers widely expect it to eventually explode as a supernova, though when this will happen is impossible to predict with precision. It could be thousands of years from now. It could, conceivably, be much sooner. When it does go, it will produce one of the most spectacular astronomical events in human history, a supernova potentially visible in daylight from Earth. Between the cool red hypergiants and the blazing blue hypergiants lies an even rarer and more peculiar category, the yellow hypergiants. These stars, with surface temperatures between roughly 4,000 and 8,000 degrees Kelvin, occupy a strange and unstable region of the Hertzsprung-Russell diagram that astronomers have dubbed the yellow evolutionary void. This region is called a void because stars do not remain in it for long. The physics of stellar structure makes this temperature and luminosity range deeply unstable, and stars that enter it are quickly driven to evolve in one direction or another, either cooling further toward the red supergiant branch or heating up as they shed mass and move blueward. Yellow hypergiants are extraordinarily rare. Only a handful are known in the entire Milky Way. One of the best studied is Rho Cassiopeiae, a yellow hypergiant located roughly 11,600 light-years from Earth in the constellation Cassiopeia. Despite its great distance, Rho Cassiopeiae is one of the brightest stars visible to the naked eye, shining at roughly magnitude 4.5 during its quiet phases. Its luminosity is estimated at around 500,000 times that of the Sun, and its radius is roughly 400 to 500 solar radii. What makes Rho Cassiopeiae particularly interesting is its history of dramatic outbursts. In the year 2000, the star underwent a massive dimming event, dropping by about a full magnitude in visible light over the course of several months. Spectroscopic observations revealed that the star had ejected a shell of material containing roughly 3% of a solar mass. The ejected material was moving outward at roughly 35 kilometers per second. The star's surface temperature dropped by thousands of degrees during the event, temporarily transforming it from a yellow hypergiant into something resembling a cool red supergiant. Rho Cassiopeiae has a history of such eruptions. Records suggest similar events occurred in 1946 and possibly earlier, suggesting that these outbursts are a recurring feature of the star's unstable existence. Another remarkable yellow hypergiant is HR 5171a, also known as V700 and 66 Centauri, located roughly 11,700 light-years from Earth in the constellation Centaurus. HR 5171a is among the 10 largest stars ever measured, with a radius estimated at roughly 1,060 to 1,160 solar radii. But what makes this star truly unusual is that it has a close companion star that is physically touching it. The two stars are in what astronomers call a contact binary system, orbiting so close together that their surfaces overlap. Observations with the European Southern Observatory's Very Large Telescope Interferometer have confirmed this intimate arrangement. The two stars are expected to eventually merge, and when they do, the result could be a catastrophic explosion or a dramatic transformation in the star's properties. The yellow hypergiants are thought to be post-red supergiant stars, objects that have already passed through the red supergiant phase and are evolving back toward higher temperatures as they lose mass. This evolutionary pathway carries them through the yellow evolutionary void, a transit that is brief and violent. The term yellow void was coined by astronomers Cornelis de Jager and Hans Nieuwenhuizen, who recognized that the region of the Hertzsprung-Russell diagram occupied by yellow hypergiants is a zone of deep atmospheric instability. Stars in this region experience a phenomenon called the modified Eddington limit, where the combined effects of turbulent pressure, pulsation, and the high opacity of partially ionized hydrogen in the stellar atmosphere conspire to make the star profoundly unstable. The atmospheric density inversions that result can trigger massive ejections of material, as the star's outer layers are literally unable to maintain a stable configuration. One of the most compelling examples of a star caught in the act of traversing the yellow void is IRC plus 10,420, a remarkable object located roughly 15,000 light-years from Earth, also known as 1,302 Aquili. This star has been observed to increase its surface temperature over the past several decades, evolving visibly blueward across the Hertzsprung-Russell diagram on a timescale accessible to human observation. In the 1970s, it appeared as a cool yellow or orange hypergiant. By the early 2000s, its temperature had risen by several thousand degrees. It is surrounded by a complex shell of ejected material that bears a striking resemblance to the nebula around VY Canis Majoris, leading astronomers to propose that IRC plus 10,420 represents a more advanced evolutionary stage of a star similar to VY Canis Majoris. If this interpretation is correct, then VY Canis Majoris may eventually evolve through the yellow hypergiant phase, pass through the luminous blue variable stage, and ultimately become a Wolf-Rayet star, tracing a complete evolutionary arc from the reddest and largest stars to the hottest and most compact. The instabilities that plague yellow hypergiants, their pulsations, their eruptions, and their dramatic changes in temperature and brightness are all symptoms of a star struggling to find equilibrium in a region of stellar parameter space where equilibrium simply does not exist. They are passing through, as quickly as physics will allow, toward whatever comes next. And what comes next, for the most massive of these stars, is one of the most extraordinary transformations in all of astrophysics. It is the moment when a massive star, having shed its outer envelope through winds, eruptions, and the slow stripping of its hydrogen-rich atmosphere, finally reveals its blazing, nuclear-forged core to the universe. It is the moment when a hypergiant becomes a Wolf-Rayet star. The story of how we came to understand these remarkable objects begins in 1867 in the dome of the Paris Observatory, where two French astronomers were about to stumble upon one of the most important discoveries in the history of stellar astrophysics. The Paris Observatory, founded in 1667 under the reign of Louis XIV, was one of the great centers of astronomical research in Europe. By the 1860s, the observatory had acquired a formidable 40-centimeter Foucault telescope, and the young science of astronomical spectroscopy was beginning to open new windows on the nature of the stars. Charles Wolf, born in 1827 in the town of Forges in northeastern France, had been working at the observatory for years. He was a meticulous observer, the kind of scientist who valued precision and systematic work. His colleague Georges Rayet was younger, born in 1839 in Bordeaux, and was working at the observatory as an assistant. Together, they were conducting a systematic spectroscopic survey of bright stars, part of a broader effort to catalog the spectral properties of as many stars as possible. The tools available to them were primitive by modern standards. Astrophotography was in its infancy, and photographic spectroscopy was even newer. The first spectrographs of stars other than our sun had only been recorded in 1863 by William Huggins and William Miller in England. And those early photographs showed only the broad continuum of starlight without the fine detail of absorption or emission lines. Photographic spectra with clearly resolved spectral lines would not be achieved until 1872, 5 years after Wolf and Rayet's discovery. What Wolf and Rayet were doing was visual observation, looking through the eyepiece of the telescope at the spectra projected by a prism and recording what they saw by hand. On that night in 1867, they turned their telescope toward 3 eighth magnitude stars in Cygnus, stars now catalogued as HD 100 and 91,765, HD 100 and 92,103, and HD 100 and 92,641, and later designated WR 134, WR 135, and WR 137, respectively. What they saw in the spectra of these stars was unlike anything that had been observed before. Most stars display absorption lines in their spectra, dark lines produced when atoms in the star's outer atmosphere absorb specific wavelengths of light emitted from the surface below. But these 3 stars showed something completely different. Their spectra were dominated by broad, bright emission bands, lines of light rather than darkness, spread across wide swaths of wavelength. The emission lines were not narrow and sharp, as one might expect from a glowing gas cloud, but instead were dramatically broadened, spread out, as if the emitting material were moving at enormous speeds. Wolf and Rayet had no way of knowing what they were looking at. The physical mechanism behind these extraordinary spectra would not be understood for decades. It was not until 1929 that astronomers attributed the broadening of the emission lines to the Doppler effect, concluding that the gas surrounding these stars must be moving at velocities of 300 to 2400 kilometers per second along the line of sight. The stars were not merely shining. They were erupting constantly and violently, driving material outward in a continuous, powerful wind. And some of the emission lines corresponded to an element that had only just been discovered in the sun's spectrum the year after Wolf and Rayet's observation: helium. The nature of these spectral lines would eventually reveal the fundamental character of Wolf-Rayet stars. These are not ordinary stars. They are the exposed, superheated cores of massive stars that have lost their outer hydrogen envelopes, either through their own powerful stellar winds or through interaction with a companion star in a binary system. What remains is a compact, ferociously hot object, burning helium and heavier elements in its core, surrounded by a thick, fast-moving wind so dense that it forms its own pseudo-photosphere. The surface temperatures of Wolf-Rayet stars range from around 20,000 Kelvin to over 200,000 Kelvin, making them among the hottest stars known. Their luminosities span from tens of thousands to millions of times that of the Sun. And their stellar winds are so powerful that they lose mass at a rate roughly 1 billion times greater than the Sun, ejecting the equivalent of one solar mass every 10,000 to 100,000 years at speeds of up to 3,000 kilometers per second. The spectral characteristics of Wolf-Rayet stars allowed astronomers to subdivide them into distinct types based on their atmospheric composition, which in turn reflects their evolutionary state. The two main categories are the WN stars, whose spectra are dominated by emission lines of nitrogen and helium, and the WC stars, whose spectra show strong lines of carbon, oxygen, and helium. A rarer third category, the WO stars, shows particularly strong oxygen emission and represents the most advanced evolutionary stage. The sequence from WN to WC to WO traces a progression of deepening exposure as the star continues to lose mass through its winds. Successively deeper layers of processed material are revealed. The nitrogen-rich WN phase exposes the products of hydrogen burning via the carbon-nitrogen-oxygen cycle. The carbon-rich WC phase reveals the products of helium burning, where helium is being fused into carbon and oxygen through the triple alpha process. And the oxygen-rich WO phase shows the innermost layers, where carbon is being processed. Further, there is also an important distinction within the WN category. Some WN stars, designated WNH, show significant hydrogen emission lines in their spectra. These are not stripped-down stellar cores. Instead, they are extremely massive stars still on the main sequence, still burning hydrogen in their cores, but so luminous and massive that they have developed Wolf-Rayet type stellar winds despite being young and hydrogen-rich. These WNH stars are among the most massive stars in the universe, and they are fundamentally different from the classical hydrogen-free Wolf-Rayet stars, even though they share similar spectral characteristics. The distinction matters because it tells us that the Wolf-Rayet phenomenon, the presence of broad emission lines from a fast, dense wind, can arise from two very different evolutionary states. Wolf-Rayet stars are rare. As of 2025, roughly 700 have been catalogued in the Milky Way, though astronomers estimate that the true number may be between 1,000 and 2,000, with many hidden behind the thick dust that pervades the galactic plane. Their rarity reflects the brevity of the Wolf-Rayet phase, which lasts only a few 100,000 years, perhaps as little as 500,000 years, a mere heartbeat in the lifetime of the galaxy. Because they burn through their fuel so rapidly, they are only found in regions of recent star formation in the spiral arms of galaxies, in young open clusters, and in giant stellar nurseries. They are never found in the old stellar populations of elliptical galaxies or globular clusters, because any stars massive enough to become Wolf-Rayets in those ancient environments would have burned out billions of years ago. Despite their distance and obscurity, 2 Wolf-Rayet stars are actually visible to the naked eye, a remarkable fact given how rare these objects are. The first is Gamma Velorum, also known as Rigor, the brightest Wolf-Rayet star in the sky, located roughly 1,095 light-years from Earth in the constellation Vela. Gamma Velorum is a complex multiple star system, but its most notable component is a Wolf-Rayet star of the W-Sate type, paired with a luminous O-type main sequence companion. The 2 stars orbit each other with a period of roughly 78 days. The Wolf-Rayet component has a surface temperature of roughly 60,000 Kelvin and a luminosity of about 170,000 suns. Its stellar wind, traveling at roughly 1,600 kilometers per second, carries away mass at a prodigious rate. Despite being over 1,000 light-years away, the system shines at an apparent magnitude of roughly 1.7, making it easily visible from the southern hemisphere. The second naked-eye Wolf-Rayet star is Theta Muscae, a triple system in the constellation Musca, the Fly, also visible from southern latitudes. These 2 stars represent the tip of the iceberg, the brightest and closest members of a population that extends throughout the galaxy's spiral arms and into the star-forming regions of neighboring galaxies. To grasp the extremes of what Wolf-Rayet stars can achieve, we need to visit one of the most remarkable places in the nearby universe, the Tarantula Nebula, a monstrous star-forming region located roughly 160,000 light-years away in the Large Magellanic Cloud, a satellite galaxy of the Milky Way. The Tarantula Nebula, also known as 30 Doradus, is the largest and most luminous star-forming region in the entire local group of galaxies. If it were located at the distance of the Orion Nebula, the closest major star-forming region to Earth, it would cover a full third of the sky and cast visible shadows on the ground at night. Its sprawling clouds of hydrogen gas stretch across 700 light-years, illuminated by the fierce ultraviolet radiation of the thousands of young, massive stars embedded within. At the heart of the Tarantula Nebula lies Roan 136, a dense cluster of young, hot, massive stars that represents one of the most extreme stellar nurseries ever observed. Within this cluster, astronomers have identified some of the most massive and luminous stars known to exist. And the undisputed champion of them all is R136 Aeon. R136 Aeon is a Wolf-Rayet star of the WN5H type, meaning it is a hydrogen-rich massive star still on the main sequence, but already displaying the powerful stellar winds characteristic of Wolf-Rayet stars. Its current estimated mass is approximately 291 times that of the Sun, making it the most massive star known as of current measurements. Its luminosity is staggering, roughly 7.2 million times that of the Sun. To put this In more visceral terms, R136 Aeon radiates more energy in approximately 4 seconds than our sun produces in an entire year. If it replaced the sun in our solar system, the Earth would be rendered completely uninhabitable almost instantaneously. The intense ultraviolet radiation would strip away our atmosphere. The year would last only about 3 weeks, and the star's radiance would outshine the sun as we know it by roughly 164,000 times in visible light alone. Though most of its output is actually in the ultraviolet, invisible to the human eye, R136 Aeon was first catalogued in 1960 by astronomers at the Radcliffe Observatory in Pretoria, South Africa. As part of a systematic survey of bright stars in the Large Magellanic Cloud, at that time, the central concentration of the Tarantula Nebula appeared to be a single extraordinarily bright object. And for years, astronomers debated whether it was one impossibly massive star, perhaps 3,000 solar masses, or a cluster of many stars blurred together by distance and the limitations of existing telescopes. The question was settled in 1985 when German astronomer Gerd Weigelt and colleagues used a technique called speckle interferometry to resolve R136A into multiple components. R136 Aeon turned out to be the brightest member of a tightly packed cluster containing dozens of extremely massive stars. Later observations with the Hubble Space Telescope confirmed and expanded this picture, revealing over 200 luminous hot stars within the Roan 136 cluster, including several others with masses exceeding 150 solar masses. The existence of R136 Aeon poses a fundamental challenge to our understanding of star formation. Standard theoretical models of how stars form predict an upper limit to stellar mass of roughly 150 solar masses. Above this threshold, the radiation pressure from the forming star should become so intense that it halts the accretion of further material, preventing the star from growing any larger. R136 Aeon exceeds this limit by a wide margin. Two explanations have been proposed. One is that the star formed through a process of competitive accretion in the extremely dense environment of the Roan 136 cluster, where the most massive star at the center of the gravitational potential, can continue to accrete material at a much higher rate than would be possible in a less dense environment. The other, more dramatic possibility is that R136 Aeon formed through the merger of two or more already massive stars in a tight binary or multiple system, a stellar collision that combined their masses into a single behemoth. R136 Aeon is not alone in its extremity. The Tarantula Nebula hosts a whole collection of monstrous stars. BA T99-98, another Wolf-Rayet star near Roan 136, has an estimated mass of 226 solar masses and a luminosity of 5 million suns. R136 Atwo and R136 A3, also within the cluster, have masses of roughly 151 and 150 and 55 solar masses, respectively. Melnick 34, a binary system near Roan 100 and 36, consists of two Wolf-Rayet stars with combined masses approaching 300 solar masses, making it the most massive binary system known. Together, these stars form an extraordinary laboratory for studying the physics of the most massive and luminous objects in the universe. The connection between hypergiants and Wolf-Rayet stars is not just thematic, it is evolutionary. Hypergiants and Wolf-Rayet stars are in many cases the same stars observed at different stages of their lives. The massive stars that begin their existence as blue O-type main sequence stars evolve through a complex and sometimes dramatic pathway that can take them through several hypergiant phases before they arrive at the Wolf-Rayet stage. This evolutionary pathway is known as the Conti scenario, named after the American astrophysicist Peter Conti, who proposed in the 1970s that Wolf-Rayet stars were the evolutionary descendants of the most massive O-type stars. In its simplest form, the Conti scenario describes a sequence of transformations. A very massive star, perhaps 50 or more solar masses, begins on the main sequence as a hot O-type star. As it evolves and exhausts its core hydrogen, it can expand and cool, passing through the blue supergiant phase and potentially reaching the red supergiant phase. During these phases, it loses mass through stellar winds and possibly through eruptive mass loss events. As it sheds its hydrogen-rich outer layers, its surface composition changes, and it may evolve blueward again, passing through the yellow hypergiant and luminous blue variable phases. Eventually, enough hydrogen is stripped away that the star's helium-rich core is exposed, and it enters the Wolf-Rayet phase. However, the actual evolutionary pathway depends strongly on the star's initial mass, its metallicity, the content of elements heavier than hydrogen and helium, whether it has a binary companion, and the rate of mass loss at each stage. More massive stars, with initial masses above roughly 40 solar masses at solar metallicity, can lose enough mass through their main sequence stellar winds that they bypass the red supergiant phase entirely, evolving directly from the main sequence to the luminous blue variable stage, and then to the Wolf-Rayet phase. Less massive stars, with initial masses of roughly 20 to 40 solar masses, may pass through the red supergiant phase first, losing their hydrogen envelopes more gradually before evolving back to hotter temperatures, and eventually entering the Wolf-Rayet stage. The metallicity of the star's environment plays a crucial role because metallicity directly affects the strength of the stellar wind. Higher metallicity means more heavy elements in the star's atmosphere, which means more spectral lines that can absorb radiation and be accelerated outward. At solar metallicity, like in the Milky Way, the winds are strong enough to strip the hydrogen envelope from stars above roughly 25 solar masses. At lower metallicities, like in the small Magellanic Cloud, where heavy elements are less abundant, the winds are weaker, and only the most massive stars, above perhaps 50 solar masses, can lose enough material to become Wolf-Rayet stars. This is reflected in the observed populations of Wolf-Rayet stars in different galaxies. The Milky Way has roughly equal numbers of WN and WC stars. The Large Magellanic Cloud, which has somewhat lower metallicity, has more WN stars and fewer WC types. And the Small Magellanic Cloud, with the lowest metallicity of the three, has almost no WC stars at all. Binary interactions add another layer of complexity. In a close binary system, a massive star can lose its hydrogen envelope not only through its own wind, but also through mass transfer to its companion. The companion's gravity can strip the outer layers of the massive star, a process called Roch-Lobe overflow, accelerating the exposure of the helium core and allowing stars of lower initial mass to reach the Wolf-Rayet stage than would be possible through wind-driven mass loss alone. This binary channel is believed to produce a significant fraction of all Wolf-Rayet stars, particularly the lower mass ones. One of the most beautiful and scientifically revealing aspects of Wolf-Rayet stars is the nebulae they create as the powerful stellar winds of a Wolf-Rayet star slam into the surrounding interstellar medium, or into material ejected during earlier stages of the star's evolution. They create structures of extraordinary beauty and complexity. These are the Wolf-Rayet nebulae, some of the most photogenic objects in the sky. The most common type of Wolf-Rayet nebula is a wind-blown bubble, a roughly spherical shell of compressed gas and dust created as the fast Wolf-Rayet wind sweeps up the slower-moving material around it. These bubbles can span tens of light years and glow brightly in optical and infrared light. One striking example is the nebula surrounding WR31A, a Wolf-Rayet star in the constellation Carina. The expanding bubble around this star is estimated to be roughly 20,000 years old and is growing at about 60 kilometers per second. But perhaps the most visually spectacular Wolf-Rayet nebulae are the pinwheel nebulae, spiral structures created by the interaction of winds in binary systems containing Wolf-Rayet stars. The prototype of this class is WR104, a triple star system located roughly 8,400 light-years from Earth in the constellation Sagittarius. The primary component of WR104 is a Wolf-Rayet star in a close orbit with a massive Ob-type main sequence companion. As the two stars orbit each other every approximately 8 months, their powerful stellar winds collide in the space between them. The region where the winds meet is compressed enough for dust to form, and the orbital motion of the system winds this dusty material into a beautiful spiral pattern, like a cosmic lawn sprinkler spinning in slow motion. WR104 gained significant attention in the popular media because of concerns about its potential to produce a gamma-ray burst aimed at Earth. The spiral nebula appeared to be oriented face-on, meaning that the rotational axis of the binary system might be pointed directly at our planet, since Wolf-Rayet supernovae are believed to be potential sources of long-duration gamma-ray bursts. And since such bursts are beamed along the star's rotational axis, this raised the alarming possibility that a future explosion of WR104 could direct a lethal beam of gamma radiation toward Earth. However, recent research led by astronomer Grant Hill at the Keck Observatory, published in 2024, has provided significant relief. Using spectroscopic observations from 3 Keck instruments, Hill determined that the orbit of the 2 stars is actually tilted at least 30 to 40 degrees out of the plane of the sky, meaning that any gamma ray burst would almost certainly miss us. The finding resolved one concern, but created a new mystery. If the orbit is tilted, why does the dust spiral appear face-on? The physics of dust formation in the colliding wind region must be more complex than previously assumed. Another extraordinary Wolf-Rayet pinwheel system is WR-140, a binary consisting of a Wolf-Rayet star and a massive O-type companion in a highly eccentric orbit with a period of about 7.94 years. The orbit is so eccentric that the distance between the 2 stars varies enormously, from roughly 30 astronomical units at their farthest to just a couple of astronomical units at closest approach. Every time the 2 stars swing close together at periastron, the resulting collision of their winds produces enormous quantities of dust that form a new shell, expanding outward from the system. The dust forms only during the close approach, when the stellar winds are compressed strongly enough, and then expands outward, forming a ring that continues to grow as the years pass. Images from the James Webb Space Telescope, released in October of 2022, revealed at least 17 concentric dust shells surrounding WR-140, each one representing a single orbital passage over roughly 130 years of orbital history. The image was breathtaking. It looked like the growth rings of a cosmic tree, each ring a record of a moment when 2 stars drew close, and their winds collided in a fury of compressed gas and freshly formed dust. The nested shells were remarkably uniform in spacing, confirming the regularity of the orbital period, and they extended outward for tens of thousands of astronomical units. The image was one of the most visually stunning early results from JWST and demonstrated the extraordinary potential of the telescope for revealing the detailed structures of stellar winds and nebulae. The research team, led by Ryan Lau of the National Science Foundation's Noir Lab, noted that the dust produced by WR-140 is carbon-rich, and that each shell contains enough dust to account for a significant fraction of the total dust production in the interstellar medium. In galaxies with fewer heavy elements, where other sources of dust are rare, systems like WR-140 might be among the primary manufacturers of the interstellar dust that serves as the building blocks for rocky planets and organic molecules. The material ejected by Wolf-Rayet stars is far from being mere waste. The winds of Wolf-Rayet stars are enriched with the products of nuclear fusion, heavy elements like carbon, nitrogen, and oxygen that were synthesized in the star's core and dredged up to the surface by convection and mass loss. Among these elements is luminous 26, a radioactive isotope produced during hydrogen burning via the carbon-nitrogen-oxygen cycle. Luminous 26 has a half-life of roughly 750,000 years, and its decay produces gamma-ray photons at an energy of 1.8 million electron volts. This emission has been detected across the Milky Way by gamma-ray telescopes, and Wolf-Rayet stars are believed to be one of the primary sources. The luminous 26 produced by Wolf-Rayet stars is particularly important because traces of it have been found in meteorites, suggesting that the early solar system may have been seeded with material from a nearby Wolf-Rayet star. More broadly, Wolf-Rayet stars are among the most important contributors to the chemical enrichment of the interstellar medium. They inject huge quantities of processed material into the galaxy, providing the raw materials for future generations of stars and planets. The carbon atoms in your body, the oxygen you breathe, the nitrogen in the air. Much of this material was forged in the nuclear cores of massive stars and distributed by the winds and explosions of objects like hypergiants and Wolf-Rayet stars. In this very literal sense, we are the children of these violent stellar titans. Their deaths fertilized the galaxy, and from the debris of their passing, new worlds were born. The ultimate fate of a Wolf-Rayet star is, almost invariably, a core collapse supernova. Having exhausted its hydrogen and worked its way through the fusion of helium, carbon, neon, oxygen, and silicon, the star eventually develops an iron core. This progression through the elements, sometimes called the onion shell structure, because each element occupies a concentric layer around the core, proceeds at an accelerating pace. The hydrogen burning phase lasted millions of years. Helium burning lasts hundreds of thousands of years. Carbon burning lasts perhaps a few hundred years. Neon burning for a few years. Oxygen burning for a few months. And silicon burning, the final stage, lasts only about a day. In the last 24 hours of a massive star's life, the core furiously fuses silicon into iron, the most tightly bound of all atomic nuclei. Iron is the end of the line for nuclear fusion, because fusing iron requires energy rather than releasing it. There is nowhere left to go. The nuclear furnace that has sustained the star for millions of years has finally run out of fuel. Once the iron core exceeds a critical mass, roughly 1.4 solar masses, the Chandrasekhar limit, it can no longer support itself against gravity. The core collapses in a fraction of a second, plummeting inward at a significant fraction of the speed of light. The infalling material rebounds off the impossibly dense core, generating a shockwave that tears the star apart in a supernova explosion. But for the most massive stars, particularly those that have been through the Wolf-Rayet phase, the explosion can be even more dramatic because Wolf-Rayet stars have lost their hydrogen envelopes. Their supernovae are classified as type Ib or type Ike, depending on whether helium is present in the explosion spectrum. Type Ib supernovae show helium, but no hydrogen. Type Ike supernovae show neither. These hydrogen-stripped supernovae are directly linked to Wolf-Rayet stars, and indeed, the connection between Wolf-Rayet stars and type Ib and Ike supernovae was one of the key predictions of the Conti scenario. For the very most massive Wolf-Rayet stars, there is an even more exotic possibility: the instability supernova in stars with helium core masses between roughly 65 and 135 solar masses. The core can become so hot, exceeding roughly 1 billion degrees Kelvin, that the photons produced by nuclear reactions begin to convert into pairs of electrons and positrons, a process called pair production. This is a direct consequence of Einstein's famous equation relating energy and mass. When a photon has enough energy, it can spontaneously convert into a particle-antiparticle pair, transforming radiant energy into matter. The problem for the star is that this process converts thermal energy, the very energy that was providing radiation pressure to support the core against gravity, into the rest mass of newly created particles. The radiation pressure drops. The support is lost. The core contracts violently. This contraction heats the core even further, triggering a runaway thermonuclear explosion so powerful that it completely destroys the star, leaving no remnant behind, no neutron star, no black hole. Nothing but an expanding cloud of debris enriched with the products of explosive nuclear burning, including large quantities of radioactive nickel-56 that power an extraordinarily bright light curve. These pair-instability supernovae would be among the most powerful explosions in the universe, potentially hundreds of times brighter than ordinary supernovae and visible across enormous cosmological distances. None has been definitively confirmed in the nearby universe, though several candidate events have been identified among superluminous supernovae observed at high redshift. They are expected to have occurred more frequently in the early cosmos, when the first generation of stars, born from pristine hydrogen and helium gas, with no heavy elements to drive mass loss through winds, could grow to masses of several hundred solar masses before dying. These primordial giants may have been the first objects to enrich the universe with heavy elements, setting the stage for the more complex chemistry that would eventually give rise to rocky planets and life. For stars that are not quite massive enough for a pair-instability supernova, the core collapse leads to the formation of either a neutron star or a black hole. The most massive Wolf-Rayet stars are expected to leave behind black holes because their cores exceed the maximum mass that a neutron star can sustain. In some cases, particularly if the star is rotating rapidly, the collapse may produce a long-duration gamma-ray burst, one of the most energetic events in the universe. A gamma-ray burst from a collapsing Wolf-Rayet star can briefly outshine the entire observable universe, concentrating its energy into two narrow jets that punch through the remnants of the exploding star and blast out into space. The connection between Wolf-Rayet stars and gamma-ray bursts is supported by observational evidence. Several Type Ike supernovae have been found in association with gamma-ray bursts, and the properties of these supernovae are consistent with the explosion of a stripped envelope Wolf-Rayet star. The first definitive link came in 1998, when a supernova designated SN 1998 BW was found at the location of a gamma-ray burst detected by the Beppo SAX satellite. Since then, a number of similar associations have been identified, cementing the connection between the death of massive hydrogen-stripped stars, and these extreme high-energy events. However, the conditions required to produce a gamma-ray burst, particularly rapid rotation of the core, are not always met, and most Wolf-Rayet supernovae are expected to produce ordinary supernovae rather than gamma-ray bursts. The angular momentum of the core, the strength of the magnetic field, and the metallicity of the star all play roles in determining whether the collapse produces a jet-driven explosion or a more conventional spherical one at solar metallicity, like that of the Milky Way. Stellar winds may be strong enough to carry away the star's angular momentum over time, slowing the core's rotation and reducing the likelihood of a gamma-ray burst. This could explain why gamma-ray bursts have been observed preferentially in low metallicity galaxies, where weaker winds allow the core to retain more of its spin. The question of which stars produce gamma-ray bursts and why remains one of the active research frontiers in high-energy astrophysics. And then there is the possibility that some of these massive stars do not explode at all. In recent years, astronomers have begun to accumulate evidence that some stars above a certain mass threshold, perhaps around 17 solar masses, may collapse directly into a black hole without producing a visible supernova. The star simply vanishes. One candidate for such an event is N6946b Hone, a star in the spiral galaxy NGC 6946, also known as the Fireworks Galaxy, because of the unusually large number of supernovae that have been observed there. N6946b Hone was observed as a luminous hypergiant in Hubble images from 2007, shining with a luminosity of roughly 1 million suns. Then, sometime between 2009 and 2015, it disappeared. No supernova was detected. No brightening event was observed. The star appears to have simply imploded, swallowed whole by its own gravity, collapsing into a black hole without the fanfare of an explosion. Stephen Smart of Queen's University Belfast has proposed that this type of failed supernova may actually be quite common among the most massive stars. If his hypothesis is correct, stars heavier than roughly 17 solar masses, which includes most hypergiants, may preferentially end their lives through direct collapse rather than through a visible supernova explosion. This could help explain a long-standing puzzle in astrophysics: the so-called red supergiant problem, the observation that the most luminous and most massive red supergiants seem to be missing from the progenitor images of observed supernovae. If the most massive red supergiants collapse silently into black holes rather than exploding, their absence from the supernova record makes sense. The idea remains controversial, and alternative explanations have been proposed, but it opens the haunting possibility that some of the galaxy's most magnificent stars end their lives not with a bang, but with a silent, invisible collapse, their light extinguished forever as they disappear behind the event horizon of a newly formed black hole. And so we arrive at the question that draws so many eyes to the night sky. What about Betelgeuse, the famous red supergiant that marks the shoulder of Orion, visible to billions of people every winter night? is one of the most prominent and well-studied massive stars in the galaxy, located roughly 640 to 700 light-years from Earth. Betelgeuse is close enough and large enough that astronomers have been able to directly image its surface, revealing a boiling, churning disk of convective cells. Its radius is estimated at roughly 640 to 764 solar radii, making it smaller than VY Canis Majoris, but still enormous by any standard. If placed at the center of our solar system, it would extend to somewhere between the orbits of Mars and Jupiter. In late 2019, Betelgeuse captured worldwide attention when it began to dim dramatically over the course of a few months. It dropped from its normal brightness as one of the top 10 brightest stars in the sky to outside the top 20. Dimmer than it had been observed in over a century. Media speculation was immediate and enthusiastic. Was Betelgeuse about to explode? Were we about to witness a supernova from our front yards? The answer, as it turned out, was no. The great dimming of Betelgeuse, as the event came to be known, was eventually attributed to a combination of factors. Observations with the Hubble Space Telescope and other instruments revealed that the star had experienced a massive surface ejection event, blowing off a large chunk of its visible surface. This ejected material cooled as it moved away from the star, forming a cloud of dust that partially blocked the starlight from reaching Earth. The timing of this dust cloud coincided with a natural minimum in the star's pulsation cycle, amplifying the dimming effect. By spring of 2020, the star began to recover, and by 2023, it had actually brightened to an unusually high magnitude, reaching the 7th brightest star in the sky. More recently, in 2025, astronomers confirmed what many had long suspected. Betelgeuse has a companion star. Nicknamed Betelgeuse, formerly designated Siwirha, this smaller star orbits Betelgeuse in a tight orbit, completing one revolution roughly every 2,100 days. The companion is believed to be a low-mass star, probably less than 1.5 solar masses, and it orbits so close to Betelgeuse that it actually passes through the outer atmosphere of the red supergiant. As it moves through this diffuse material, it creates a wake, like a boat moving through water, that disturbs the gas around Betelgeuse and may contribute to the star's long-term brightness variations. The discovery of this companion provides a new explanation for the mysterious 6-year periodicity in Betelgeuse's brightness that had puzzled astronomers for years and reduces, though does not eliminate, the relevance of the Great Dimming as a potential supernova precursor. Betelgeuse will eventually explode as a supernova. This is not in doubt. But when? Current estimates range widely, from a few tens of thousands of years to perhaps several 100,000 years. A study published in June 2023, analyzing the star's pulsation periods, suggested that Betelgeuse might be in a late stage of core evolution, potentially burning carbon, which would place it closer to its end than previously assumed. However, the majority of astrophysicists remain cautious about such claims. Whether the star has begun carbon fusion, a crucial question for predicting the supernova timeline, depends on precise knowledge of the star's current core state, which we simply do not have. What we can say is that a supernova within our lifetimes, while not impossible, is extremely unlikely. The odds have been estimated at roughly 1 in 4,000 that Betelgeuse has already exploded, and we are simply waiting for the light to reach us. Those are long odds, but not impossibly long. When it does happen, however, it will be one of the greatest astronomical spectacles in human history. Modeling suggests that the explosion would unfold in stages visible from Earth. First, neutrino detectors around the world, facilities like the Super Kamiokande in Japan and IceCube at the South Pole, would register a sudden burst of neutrinos from the collapsing core, providing advance warning hours before any visible change. Then, over a period of roughly 10 days, the star would brighten enormously, rising from its normal brightness to a peak luminosity roughly equivalent to the half moon. At peak, it would be easily visible during the day, a brilliant point of light in the sky that could be seen even through thin cloud cover. This peak brightness would persist for a few weeks before beginning to decline, first slowly, then more rapidly. The star would remain visible to the naked eye at night for perhaps 2 years as it gradually faded, eventually leaving behind only a glowing supernova remnant visible through telescopes. And thanks to its distance of roughly 650 light years, a Betelgeuse supernova would pose no significant threat to life on Earth. The energetic radiation and particles would be greatly attenuated by distance. There would be no mass extinctions, no ozone depletion, no harmful effects on our biosphere. Just a glorious show in the night sky, a once-in-a-civilization event that every human on Earth could witness simply by looking up. The study of hypergiants and Wolf-Rayet stars is, in the deepest sense, the study of the engines that drive the evolution of galaxies. These stars are the primary manufacturers of the heavy elements that make up rocky planets, organic molecules, and ultimately, life itself. Their winds and explosions sculpt the interstellar medium, compressing gas clouds and triggering new episodes of star formation. Their deaths seed the galaxy with the raw materials for future worlds. Without stars like these, the universe would be a far simpler and far emptier place, a cosmos of hydrogen and helium, and not much else. There is a profound irony in this. The very stars that are least suited to hosting life, the stars whose radiation would sterilize any planet within 100 light years, whose lifetimes are too short for biological evolution to even begin, are the very stars that make life possible elsewhere. It is the death of hypergiants and Wolf-Rayet stars that creates the carbon, oxygen, nitrogen, and iron that constitute the substance of living things. Every atom of calcium in your bones was forged in the core of a star far more massive than our sun. Every atom of iron in your blood was synthesized in the last seconds of a massive star's life, fused from silicon in the desperate final moments before the core gave way. The gold in a wedding ring, the iodine in your thyroid, the phosphorus in your DNA. All of it was created either in the final moments of a massive star's collapse or in the cataclysm of the supernova itself, flung outward into the interstellar medium to be incorporated, billions of years later, into a rocky planet orbiting a quiet yellow dwarf in an unremarkable spiral arm of the galaxy. They are also, in a way, the most dramatic illustrations of the fundamental tension at the heart of stellar physics, the battle between gravity and radiation. Every star is a contest between these two forces, and in most stars, the contest proceeds at a measured, predictable pace for billions of years. In hypergiants and Wolf-Rayet stars, the contest is desperate, violent, and brief. These stars are burning themselves alive, spending their nuclear inheritance with reckless abandon, blazing through their allotted fuel in what amounts to a cosmic instant. They are, by any measure, the most spectacular objects in the stellar zoo. And though they are rare, though they are fleeting, though most of them are so distant that they can only be seen through the most powerful telescopes ever built, they have shaped the galaxy we live in and the atoms we are made of. The next time you look up at the winter sky and find the familiar orange glow of Betelgeuse, or trace the curve of Orion's shoulder, remember that you are looking at a star that is about to die, perhaps not soon by human standards, but soon by the reckoning of the cosmos. And when it goes, it will leave behind a legacy of heavy elements, a glowing remnant nebula, and perhaps a spinning neutron star or a silent black hole. And from the material it scatters across the galaxy, new stars will form, and around some of those stars, new planets, and on some of those planets, perhaps, new eyes will look up at a new sky and wonder at the light. We live in an age when the tools available to astronomers are more powerful than at any point in human history. The James Webb Space Telescope is peering into the hearts of stellar nurseries with a clarity that would have seemed like science fiction even a decade ago. The Atacama Large Millimeter Array is mapping the molecular outflows of dying hypergiants at radio wavelengths, revealing structures billions of miles across. The European Space Agency's Gaia mission is measuring the positions and distances of billions of stars with unprecedented precision, resolving long-standing debates about the sizes and luminosities of the galaxy's most extreme stellar inhabitants. And the next generation of ground-based observatories, including the extremely large telescope currently under construction in Chile, will push the boundaries even further, potentially allowing us to resolve the surfaces of red hypergiants in other galaxies and study the winds of Wolf-Rayet stars in environments very different from our own. The story of hypergiants and Wolf-Rayet stars is far from over. Each new observation reveals new questions, new puzzles, and new reasons for wonder. We do not yet fully understand what triggers the giant eruptions of luminous blue variables. We cannot yet predict with confidence which massive stars will end their lives as supernovae, and which will collapse silently into black holes. We do not know for certain whether the upper mass limit for stars is set by the physics of accretion, the dynamics of stellar mergers, or some other process entirely. And we do not know what surprises the next nearby supernova, whenever it comes, will hold for us. What we do know is this: the universe is built on the ashes of giants, the atoms in your body, the ground beneath your feet, the air you breathe. All of it was forged in the nuclear fires of massive stars and distributed across the cosmos by their spectacular deaths. The hypergiants and Wolf-Rayet stars are the architects of the periodic table, the engines of galactic chemical evolution, the cosmic factories that produce the raw materials of life. They are rare, they are violent, they are fleeting, and they are absolutely essential. If you enjoyed this journey through the most extreme stars in the galaxy, please take a moment to like this video and subscribe to the channel. Leave a comment letting us know which of these incredible stars fascinates you the most. Is it the red giant VY Canis Majoris, the unstoppable furnace of R136 Aeon, or the dramatic eruptions of Eta Carinae? We would love to hear from you. Thanks for watching, and we will see you next time.